And up next, we'll welcome Abhidej from the University of Illinois at Urbana-Champaign.
Hi. First, I would like to thank CCAT for inviting me to join this event. So my background is a pavement engineer, and my research work is more focused on the infrastructure side. So today I will share how I built a magnetic roadway to enhance driver assistance system. So CCAT has been providing the funding for this project since 2023, and this research work is supervised by Professor Lessler. So today I will share 4 parts, starting with the transportation safety motivation and concept of pavement enclosed signage. And I will share some experimental results and research findings. So the primary driving maneuver that lead to fatalities in the US is about nearly 50% caused by roadway departure. And the critical area is more on the rural roads, which more than 60% of roadway departure occur in the rural roads. And the critical reason that lead to road accidents, I think everyone in this room might know it. It is the human mistakes. More than 90% of road accidents caused by human error. These errors include recognition error, such as inattentive driving and distraction, decision error, such as speeding or driving too fast for the conditions. So recently, in the last decade, we have a good promising technology we call advanced driver assistance system. This system can address the human limitation and can improve roadway fatalities for the last decade. However, when the road marking is covered with snow or the lane marking is obstructed, these systems are not reliable since they are heavily rely on the visual sensor. So I'm trying to create an electromagnetic-based communicable roadway that can convey a crucial safety information or instruction to the driver that overcome the weather limitation and minimize driving mistake caused by human error. So this is the new idea. The initial idea was in 2002 in California, Berkeley. They used a permanent magnet to put on the roadway for assist bus lateral guidance and precision docking at the bus station to reduce workload of the driver. And later, one of the PhD students in my research group, he found that we don't necessarily to embed the actual permanent magnet. We can also disturb the local Earth electromagnetic field by embedding the high magnetic permeability material in a pavement layer. So he put some of materials such as steel fiber, iron filling, and mesclun ribbon, and this disturb the local Earth magnetic, and the sensor can also detect the lateral position from this material. However, after that, we received some feedback that how about the temporary revised traffic area such as the work zone, because we need to change the electromagnetic signature in that area. So right now I'm focused more on the temporary deployment. So I think the answer is the coating application. So I will I was trying to put demagnetizable material and coat it on the roadway. So there are two main components of the pavement enclosed signage. The first component is the sensor. So this sensor should be able to sense electromagnetic signature in all weather conditions, and it should be computationally light for real time and be accurate for lateral position within the lane. And another part is the electromagnetic signatures. It can be either permanent deployment or temporary deployment. On the left chart here, show the ideal condition where the truck located at center of the lane. And on the right chart, it shows that when the truck is about to leave out of the lane. So why would temporary deployment matter? So according to the work zone fertility statistic for the last decade, we found that the fertility trends in this area is continue climbing up. And the two major factors contributing to this accident is the unsafe speed condition and unsafe lane change, which occur mostly in a taper and approach section prior to the construction area. And the main reason is the driver error and distraction and inattention. So several countermeasures have been implemented in this area, but according to the statistic, the trend never go down for the last decade. So we found a simulation study show that the in-vehicle message warning system could outperform the conventional measures. So my focus is on making the pavement enclosed signage that can be used to assist the in-vehicle message warning system. So this is the typical work zone layout. So we're trying to build a smart work zone warning system to address driver inattentiveness and unsafe speed condition and unsafe merging condition. Imagine if I place the pavement enclosed signage for the speed warning for the vehicle approaching the advanced warning area, and then I put the pavement enclosed signage for the merge left for the lane merge warning in the several patterns. And we can also provide the assist lane shift maneuver during the transition area, and another in-vehicle speed warning before approaching the workspace. And the system can also provide the end of work zone warning when the vehicle exits the work zone area. So this is the schematic how we provide the in-vehicle speed warning. So if I place the electromagnetic strip in transverse direction, and as the vehicle approaches this strip at the constant spacing, we can predefine the time period for the vehicle to approach this strip. If the vehicle approaches this strip at lower time than the predefined time period, it means that the vehicle is overspeeding. So then the system can trigger the overspeed warning alert. This is another scenario for the lane merge warning. We can place the electromagnetic strip in a shift pattern. For example, in this case, it's shift from right to left. And as the vehicle approaches this strip, normally the vehicle must have at least 3 sensors located on the bumper. So this system, this sensor can be recheck each other, and it can trigger the merge left warning to the vehicle. So how I make a coating of electromagnetic signature on the roadway. So I use the ferromagnetic oxide material with the conventional epoxy paint marking. And after I apply on the specimen, I heating the specimen up to the temperature above the Curie temperature of the ferromagnetic oxide material that I use. So it's mean like I magnetizing the roadway by reaching the Curie temperature, and I place the permanent magnet on top to magnetize to realign the magnetic moment of the marking. And then I reduce the temperature down before remove the magnet bar to capture the magnetic moment of this pavement marking. So I will share some lab works, but there are 3 series of lab experiments that I have done for the last 3 years. So first I did a lab experiment to validate the detectability of the electromagnetic signal from the electromagnetic pavement marking. And then I developed several pavement encode signage in different patterns on the top left figure for the construction work zone warning. And this time we put the sensor on the actual vehicle and test at different speed varying from 15 miles to 60 miles per hour, and different vehicle motions and different weather conditions include when the pavement covered with snow or sleet. And last year we focused on the reliability and accuracy of the system. So I put the electromagnetic strip along the horizontal curve of the actual rural road. The 2 parameters that I focus in this test is the lateral offset position of the vehicle to the center of the lane and the back calculated speed of the vehicle. So I put 12 of electromagnetic sensor on the vehicle bumper at the bottom row for detect the electromagnetic signatures, and I put 3 of the electromagnetic sensor on the top row to capture the electromagnetic interference and use for rejection of fault detection. So this is the raw data from the experiment. I believe no one could help me identify where is the first electromagnetic strip in this chart, because there are a lot of interference and noise from environment nearby the roadway. So the most challenging part of this experiment is the signal filtering and signal processing. So I apply a fast Fourier transformation to check the electromagnetic spectrum of the test data. And we found that there are 2 major interference sources. The first one is the electric current from the power line located nearby the road at 60 Hertz. And another one is the harmonic wave of the wheel and tire rotations. So after I apply the digital filter to filter those interference out, I can achieve and detect the electromagnetic response from my electromagnetic strips. And even we test at poor weather condition when the road partially covered with snow or even fully covered with snow, we can detect the electromagnetic response. And this is the comparison chart between the visual detection and electromagnetic detection from the test that we did on the horizontal curve. We found that the difference between the visual detection and electromagnetic based detection error is around 1 inch. And this is the validation of the vehicle speed trace, comparing the GPS sensor with the back calculation of the electromagnetic strip. And the speed error is around less than 1 mile per hour. So this chart shows the successful detection rate comparing the visual detection and electromagnetic based detection. In normal weather conditions, they are not much different from the two systems, but when the roadway covered with snow or ice sheet, we found that the electromagnetic based detection could outperform the visual detection. And in terms of accuracy, this one is the average absolute lateral offset deviation from the visual sensor compared with the electromagnetic based sensor. So we can achieve about 1 inch lateral error between the two systems, and we can achieve less than 1 mile per hour error compared with the GPS system. So in summary, the electromagnetic material in pavement with the magnetometer array could enable V2I communication with the focus on peak sensor response detect over EM strip. And the ferromagnetic oxide, in this case, I use the chromium dioxide with the 20% of the pavement marking, can be used to create discrete programmable electromagnetic signature on pavement surface. And the temporary pavement encode signage was detectable and interpretable during high-speed tests under adverse weather conditions with low speed error deviation and lateral error deviation. That's all for my presentation today. Thank you.
Thank you so much, Happy-Dej. We have time for one question.
So magnetic field decays very rapidly with distance. And my first question is what kind of magnetic field are you detecting? And the second question is you are mounting these sensors on bumper.
Yes.
And for realistic applications, sensors need to be integrated into the frame or somewhere. And there are many parts. Frame itself too emits magnetic signature, and it's unrealistic to degauss all of those, the frame elements or structural elements. So, and also, of course, there is interference from other components too, like a motor. And how do you account for or separate, signature from the pavement from structural or component, magnetic signatures?
So the first question is the
Gauss level at the sensor location.
Okay. So I put the single axis front-gate electromagnetic sensor on and capture the signal in vertical direction. And actually, Volvo car company have done some of these tests before, and they put 5 sensors in their car, and they also validate the detectability of the electromagnetic signal from the permanent magnet. But for me, the difference between the permanent magnet and my electromagnetic pavement marking is that the electromagnetic signature of my pavement marking is like within nano Tesla unit, like around 100 to 1,000 nano Tesla, and we try to capture change in electromagnetic flux in vertical direction. And this one is we can distinguish between our electromagnetic pavement marking from the metallic material surrounded by the vehicle, because the electromagnetic flux of metallic material is strong. It's like more than 10 times strong than our electromagnetic signal, and the coverage area of the coverage area of electromagnetic flux for metallic material is more broader than our electromagnetic signature. So we try to capture the small change in electromagnetic flux from the pavement. And I put 2 rows of sensors the top sensor also detect the interference because let me say this way. We distinguish the electromagnetic signature from the pavement from the other EM source by assume that if the bottom sensor detects the electromagnetic response, it does not necessarily to capture the electromagnetic signature from the pavement. But if the top row sensor detect, if the top row sensor did not detect the electromagnetic signal at the same time as the bottom row that detect the electromagnetic signal, that is a condition when this is a true signal. But if both rows detect the same the same signal at the same time, like within 10 milliseconds, we assume that is the noise or interference from other source. Thank you.
Thank you so much.